So today we're talking about the force on a charged particle in a magnetic field. So let me preface this discussion with a few things that I want to start out with. Last semester when we did electric fields, we began our conversation by using Coulomb's law as our starting point. And we talked about the interaction of statically placed charged particles and evaluated the force on those particles due to their proximity to each other. We dealt with direction based on a straightforward way of analyzing the orientation of the particles relative to an XYZ plane. And we basically just drew a line between any two particles and identified the fact that the force was going to be positive and or negative, determining whether it was an attractive force or a repulsive force. You guys remember all that garbage from Coulomb's law? We started with the concept that the charges applied forces to other charges and then developed a theory of the electric field from there, defining the electric field based on the size of the force between 2-point charges. You guys recall that? And so we based our description of the electric field on the force that was applied. We can't do that with the magnetic field. So we're going to study this a bit in reverse, because determining the way charged particles interact through the magnetic field is actually the most complicated part of this. So we're going to assume the existence of a magnetic field for the beginning of our discussion, and then we'll describe where the magnetic field comes from later in a similar fashion. But what I can't do is I can't, at the beginning of this, describe for you why one particle imparts a force to another particle through the magnetic field. You need more information than I can give you right at the beginning. So we will establish that a magnetic field can be said to exist in a region of space. Now, there's a lot about this that you're not going to like, but you just have to get used to it. First, we use a capital B for a magnetic field. No capital M here, no capital E. So I do know a little bit about the reason why capital B is used, but not enough to be able to entertain any questions about it. But we will use a capital B, and it is a vector quantity. So in an equation, we will talk about the magnetic field in terms of its value. And for right now, without proof, unlike the electric field, we have a unit that is used for the magnetic field. There are two. One is the Gauss, and the other is the Tesla. Now, the Gauss and the Tesla are similar units. They are like a similar relationship as like gram and kilogram. A Tesla is 10 to the 4 Gauss. Now, I will not use Gauss in here ever, but old FRQs sometimes use Gauss. So if one slips in there, I want you to know that just convert to Tesla. We're going to use Tesla for the unit of the magnetic field. Now, I can't explain enough about this, so I'm not going to. The Tesla is a complex unit in the same way that the electric field had a complex unit. If you'll recall, the electric field unit was volt per meter or Newton per Coulomb. But there's no special name given to the electric field. The magnetic field has a special name. It's in honor of Nikola Tesla. Now, not to mention, I'm afraid I will give you false information, because I know what I think the truth is, but I haven't verified it in a lot of years. And there has been actually quite a bit of revisionist history on his life in the last 10 years, because there's been 2 major documentaries that have come out to try and talk about his life, and they're in conflict. So I'd say look it up. Let's get back to the basics of this, and I want to talk to you about the force on a charge-carrying particle as it passes through a magnetic field. And here is the most important part about magnetic fields. They are dynamic. Unlike everything we did first semester, which was static, the magnetic field is a dynamic system. And to understand, or at least to understand why that word is being used here, you need to understand just the relationship, where the force from the magnetic field comes from. So the force on a charge-carrying particle as it travels through a magnetic field is QV cross B, where Q is the value of the charge, V is the velocity of the particle, and B is the strength of the magnetic field. The X in there is not an X, it is the cross product. Cross product. Now, this should be an important, this should raise something in your mind about this idea of this force. It doesn't behave the way you might expect. A positive charge-carrying particle sitting in a powerful magnetic field experiences no force unless it's moving. So the first thing you have to understand is that all of the charged particles we talked about first semester, as long as they were stationary, they could not experience a force from a magnetic field. It's only when they're moving can a magnetic field have an effect on the motion of the charged particle. Now, later on, I'm going to blow your mind with some stuff about this, but those of you who have a recollection of first semester physics should start having the back of their their memory tingle a little bit for something I'm about to say. So let's consider just a simple, straightforward idea here that we give this particle a little bit of velocity. The size of the force is relatively simple to calculate. It's QV cross B. Do you guys remember how to deal with the cross product? Do you remember the dot product at least? We've done the dot product a lot this year. The dot product is called the scalar product. It produces a scalar. In a dot product, you're trying to see how aligned the two vectors are. A dot product is greatest when the two vectors are in complete alignment. Do you remember that? So one has to be in the direction of the other. The cross product is the opposite. The analogy that we have for mechanics is that the cross product is what we use for torque. If I want to open the door, the best way to do so is to apply a force perpendicular to the door. The door itself is a torque arm. I want to push perpendicular. I get maximum torque when the two vectors are perpendicular to each other. That's the cross product. The cross product is maximum when the two vectors are perpendicular to each other, which should suggest to you that the force is going to be based on the sine of the angle between the velocity and the magnetic field. Right? Sine is a maximum at 90, so we use the sine here because we get maximum, our maximum result for two vectors that are perpendicular to each other. Now, I want to continue this a little bit, but remember, direction of force is something you'll be asked. Magnitude, easy. QVB sine of theta, or sine of phi in this case. Magnitude, straightforward. Direction, a little bit harder. So I want to stop and talk to you about the right-hand rule, but I also want the people who aren't here to benefit from this. So let me just say a few things. You're going to need your right hand for this. We want to figure out the direction of the force using the right-hand rule. If you don't recall, you hold like your pointer finger. You hold your hand in the traditional X, Y, and Z format with your pointer finger pointing ahead of you, your middle finger off to the side, and your thumb pointing up using your right hand. The way you use your right hand to determine the resultant is to remember that pointer finger is the first vector in the equation, middle finger is the second vector in the equation, and your thumb is the result. That's how the right-hand rule works. So to determine the direction of the force, start by pointing in the direction of the velocity, which for us would be pointing upwards. And then rotate your hand until your middle finger points in the direction of the magnetic field. You need to leave your hand pointed so that your pointer finger is in the direction of the velocity, and rotate your hand until the middle finger is in the direction of the magnetic field. Now, again, the direction of the force is into the board. This should illuminate you to the idea that the magnetic force and everything having to do with magnetic field is probably going to be very three-dimensional in nature, right? For every problem involving the magnetic field, the force ends up being perpendicular to the plane created by the velocity and the magnetic field. So that will make these very three-dimensional in nature in almost every case. It's hard to do 3 dimensions on a 2-dimensional board. So for those of you who don't remember, we have a way of expressing vectors that mean into the board and out of the board. It's not particularly hard. We use a dot, and I say a dot with a circle around it to indicate out of the board, or out of the paper. I wouldn't write board if I were you, because you're writing on paper, unless of course you're writing on virtual paper. Then I don't know what you write, out of the screen, but write something. And we use a circle with an X in it to represent into the screen. Now, a couple points of context. This is expected on the exam and anticipated. So you may be asked to draw in the direction of something using this symbology. This is the accepted symbology for this class and accepted on the AP exam. The idea of the dot and the cross comes from an arrow. I want to, just think that an arrow has a pointed end, and if you think of a real arrow, it has fletching. So if it's coming at you, you see the point of the arrow as it comes at you. If it's going away from you, you see the fletching of the arrow. That is supposed to be the cross. So if we were to be told what is the direction of the force, it would be expected that you would say, okay, the force in this case is into the board and acts on the particle. Okay? Are we okay with that? Any questions? So, example, and I want to immediately tell you that if you're dealing with a field that is out of the board, they don't draw the circles. They will give you a field of dots representing the direction of the magnetic field. You don't put the circle around a group of things representing a field of vectors. You only do that for a single vector. So I would say this is my magnetic field as it points out of the screen. Everybody follow along with that? So a field of dots is out of the screen. A field of crosses or X's would be into the screen. In keeping with my my starting problem, let's have this be the arrangement. The velocity of the positive particle upwards or away from you. The direction of the magnetic field out of the board. Can you use the right-hand rule to determine the direction of the force on our charge-carrying particle in this magnetic field? So again, pointer finger in the direction of the velocity. Rotate your wrist until your middle finger points in the direction of the magnetic field, which in this case should be out of the paper or out of the board or out of the screen. And my thumb points to the right. So that would suggest that the force on the particle would be to the right. Yes, sir? Yes. Those dots represent the points of the arrow. I mean, it is too cumbersome, and they won't do it to put the circle around a field. Does that make sense to all of you guys? They just won't do it. So if you're generating a field value, we're going to have to have a lot of them, because that's what they're going to do. They're going to show an area of space filled with a magnetic field. They'll indicate the direction of this magnetic field like this, with a field of dots. Now, while we're on the subject of the force acting on this charged particle, I want to add something to the discussion, but I generally think you guys tend to need a couple of practice questions here. Do you want to try some more practice with the right-hand rule real quick? So we'll do one more. So let's change it up. All right, so changing it up a little bit. I don't want to help you. I want you to do it. So please use the... This particle experiences a force that is downwards. Now, let me be very plain about this. The force is always going to be perpendicular to the plane created by the velocity and the magnetic field. I'm saying this very carefully because I don't want to have to write it down, but I think you should. The force is always going to be perpendicular to the plane created by the velocity and the magnetic field. Right now, with all my examples, I've made the velocity and the magnetic field perpendicular to each other. They don't have to be. But the force will always be perpendicular to the plane created by the velocity and the magnetic field. Because that I want to make sure gets said. This will do. This example. The particle is going to experience a force that is perpendicular to the velocity, suggesting that the particle's path is going to turn. Correct? When the particle makes it to this new place, its velocity has changed direction. Right? Which also means the magnetic field has changed direction. But be careful, the magnetic field, still use my right hand rule, is going to be perpendicular to that velocity. Two things you need to write down. Free particles are going to have circular paths. This is a centripetal force, or causes centripetal acceleration. Second, and most important that you write down, the magnetic force can't do work on a free charge. It's perpendicular to motion. The scalar product is zero. The magnetic force can't do work on a free charge. A charge is not bound by a wire. A free charge in space that can experience a force, you can't do work on it. That means you can't start it into motion. You can't change its kinetic energy using a magnetic field.
On a free charge?
On a free charge. Free charge is important that you have that in there.
What was the first?
I'm going to have to, at some point or another, start testing you in ways that are harder. Can you try this one?
You said the index finger is the way of the magnetic field?
No.
Index is the first vector.
Index is the first vector. Magnetic field is the second vector. So velocity first. Is there any way to rotate your wrist to get your middle finger to line up with the magnetic field? No, not without bending your finger all the way backwards like this. But then, which way would you orient this? Because it would stand for all of them, right? Pay very close attention. I would argue that the angle between the velocity and the magnetic field is 180 degrees. Would you make that same argument? Q, V, B, sine 180 degrees. There are some velocities for which there is no force. The magnetic field is weird. So you can actually have a particle traveling through a region of space with a very strong magnetic field and it still experiences no force.
The sine of 180 is 0.
The sine of 180 is 0. Now, of course, it shouldn't take too much for me to say, I don't want to have to do this example. Right? We good? I don't have to do this one to show you that, that's true. It's going to be all right. But I do want to take a moment and talk about this example. The moment they're no longer in perfect alignment, they create a plane. You guys understand that, right? The moment they're not in perfect alignment, they create a plane. So if they're not co-parallel or anti-parallel, they create a plane. So I know that I tell you to make your formation of your hand all right angles. This part's important, folks. Please, please. Your pointer finger always, always is to the right of your middle finger. Never reverse them. You're never actually flipping anybody off, okay? Because you need to ensure that you understand that although the velocity is this way, I can still get to the magnetic field while keeping my middle finger to the left of my pointer finger. They define the plane. This force is out of the board. Once we start dealing with situations which are not perfectly lined up, it's easy to, especially if it's too hard to flip your wrist around, you may start flipping your fingers around. You can't do that. You have to make sure the middle finger is always to the left of the pointer finger. Okay? That defines the field. And this would have a force out of the board. Now, I have to say something here because there are some of you who are a little silly, and I want to make sure that you hear stuff. Unless I have a very eager group to learn it, I can teach it. It's not particularly hard, but you guys don't know things like what the determinant of a matrix is, and these would all have to be three-dimensional matrices. I just don't want to do the work. But if you're desperate for it, we can have an aside one day. There's something to point out too.